So if the same polyatomic ion shows up more than once on both sides, use it together. So if you see SO4 on one side and SO4 on the other side, don't count S's and O's, count SO4s. It's easier to count groups of atoms than it is to count individual atoms. Okay? And if they stayed together, we're still actually counting everything. We're not missing counting it, we're just counting it as a group. Okay? So let's show you why you'd want to do it. So first, I'm going to do this without using that technique. So I'm going to do this equation the way we learned before we learned today. Okay? So aluminum bromide and potassium sulfate make potassium bromide and aluminum sulfate. Okay? So reactants, products, I have to worry about Al, Br, K, S, and O. That's what we would have done there. So there's one Al, 3 Brs, 2 Ks, 1 S, 4 Os. On the other side, there's 2 Als, 3 S's, 12 Os, 1 K, and 1 Br. So what do you want to fix? Everything. Is that a fair statement? Everything. So it doesn't matter which one I fix first. There's nothing shows up twice. There's no reason to pick one over the other. So I'm going to fix Al by putting a 2 in front of it. That's going to change my Br to 6. That tells me I need 6 in front of KBr. Okay, that Peter? Okay, Peter, give me a second, please. Okay, that gives me my 6K, my 6Br. Now I need to fix the K over here, so I have to put a 3 here. That gives me 6 Ks, 3 S's, and 12 O4s. Okay. We still get there. 2, 3, 6, 1. So the new way. Al, Br, K, and SO4. Because SO4 stays together, why did you move? Since K stays together, since SO4 stays together, then you can count it as a unit. So I've got 1 Al, 3 Brs, 1 K, and 1 SO4. 2 Als, 1 Br, 1 K, 3 SO4s. So what do you want to fix? I can start off with Al again. It would work just the same. I can pick a different one. I'm going to pick Br. Okay.
Should we have 2 potassiums on the reactant side?
Yeah, it should be 2. These 2. Okay. So it doesn't matter which one I fix. But the key is, it makes SO4s easily to fix. So 3 in front of K2SO4. That gives me 6 Ks and 3 SO4s. See how quick that made the SO4? That's easier than 3 and 12. And that's when only one of them has a polyatomic ion. Imagine if both of them had polyatomic ions. And then to fix the K, I'd put a 6 here. 6 Ks and 6 Brs. And then I put a 2 here to get my 6 Brs and my 2 Als. And I end up in the same place. I'm just counting whole units rather than individual sulfurs and oxygens. So it's not really that different a technique. going to save us time. Could you imagine counting oxygens here? Titanium 2 hydroxide and phosphoric acid make titanium 2 phosphate and water. And oxygen shows up everywhere. But we're not going to count oxygens. Huh? Or are we? Well, we can get away with it if we do one little trick. And that's write water as hydrogen hydroxide. Why is that a trick for me? What good does that do me? Because it gives me OHs on both sides. Well, what? Isn't that water? HOH? Okay. Hydrogen hydroxide, doesn't that describe water? So I want to count the hydroxides. So I can find that there's a polyatomic ion in water, hydroxide. And by doing that, it's going to allow me to count reactants, products, Ti, OH, H, and PO4. Only counting 4 things rather than 6. And H's almost everywhere, O's everywhere. Pain to fix. So that's 1 Ti, 2 OHs, 3 H's, and 1 PO4 on the reactant side. By the way, on the homework, this was the most common mistake on writing formulas, is not putting OH in parentheses. And on the other side, it was 3 titaniums, 2 phosphates, 1 hydrogen, and 1 hydroxide. So, what do you want to fix? Titanium. So to make fix titanium, I'd have to put a 3 here, right? That would give me 3 titaniums and 6 hydroxides. Now what do you want to fix? Hydroxide. We can fix hydroxide. To have 6 hydroxides on the other one, I need 6 HOHs. That would give me 6 H's and 6 OHs. Now to fix hydrogen, I'd have to put a 2 in front of phosphoric acid. And that would give me my 6 hydrogen, and it would give me 2 phosphates. Surprise, surprise. Well, that bounced really easy, Mr. Green. That wasn't very hard. How many oxygens are on each side? Well, there's 6 here and 8 here, so there's 14, right? There's 8 here and 6 more is 14, right? So the oxygen's really balanced, but a pain to count. How about the H's? How many H's on each side? 6 here and 6 here is 12, and 6 there is 12. Okay. See how counting hydroxides and phosphates is easier than counting oxygens and hydrogens. Oxygens and hydrogens work. It's just counting the polyatomic ion makes it a little faster. You get to the same answer. Right. Next thing I want to show you involves this stuff over here. And what that thing is it's called a Hoffman apparatus, after somebody whose last name was Hoffman. Okay? And it's really pretty simple design. Okay? It's 3 tubes joined at the bottom. 2 of them are marked like graduated cylinders, measure volume. The third one is just a refill. So it gives a place for the water in here to expand, so it can expand up that tube. And the reason why the water would go up that tube is because down at the bottom, where's my zoom? Zoom too much. Right, get a focus there. Down at the bottom, these things right here are little rubber stoppers, and there's wires hooked into them. And those wires lead inside, and when I turn the power on, good things are supposed to happen. There you go. I turn the power on. Notice you get bubbles on both of them. Right? So I'm getting bubbles. Bubbles on this side, rising up. Bubbles on that side, rising up. We're collecting those bubbles. We'll see what those bubbles are later. But while we're waiting, we're going to move on into types of reactions. And the reason why we're learning to categorize things by type is because that'll allow us to predict the products. That's our ultimate goal. In a chemistry class, you expect to learn what turns into what. This is where we learn that, how we can predict it. Okay. Because there are way too many too many reactions to memorize them all. Way too many. There's millions and millions of chemicals that all interact with each other. Think about how many combinations that is. Or permutations. So we're going to see that they fall into some categories. Now, these are big, broad, general categories. There's actually subcategories of each one that your book is going to bring up. We're going to learn 5 major types. The 4 ways things can change partners. And then a 5th one. Okay. Once we categorize what type it is, that'll tell us what's going to happen. The name will tell us what's going to happen. And we do what that name says, and we'll be able to predict what it makes. If it says this falls apart, we make it fall apart. The name says falls apart. There's some we're going to be able to predict whether they happen at all. That you mix this and this together and nothing happens. That's important to know. Choosing materials. I'm going to make a boat. I should choose a material that doesn't react with water. The material that reacts with water would be a bad choice. So I'd want something that when you put it with water, there was no reaction. Now, if we're going to predict the products, we've got to be able to recognize them from just the reactants. So we're going to have to be able to categorize by reactants so that we attach a name. That name will tell us what to do to those reactants. The name tells us what to do. The names are really descriptive. We like them. Type number 1 is called a combination reaction. What would you think happens in a combination reaction? Things combine. Okay. Another name for this, I think your book uses it occasionally, is synthesis. Because both combination and synthesis have the same meaning in one key concept, and that is you put things together. Synthesis means to take all the information. Synthesize something means to take what you have and put it together in a new way. So combining means take 2 things and put them together. So that means I got 2 things when I start. They could be elements, they could be compounds. And when I'm done, I only have 1 product. Because if I combine things, I should have only 1 thing when I'm done. Is that reasonable? Name pretty descriptive? Yeah. Here's an example. Ca plus O2 makes CaO. That would be 2 elements making a compound. Something about this bother you? Bothers me. not balanced. So as we're doing this, you're going to get much better at balancing equations. Okay? We'll practice it as we start writing the equations for this. So I got two O's on my reactant side, so I need two O's on my product side, so I can put a 2 in front of that. That gives me two CAs, so I can put a 2 in front of that. And now it's balanced. Two calciums, two oxygens, and two oxygens. You don't always have to make the table. Sometimes they're easy. We want the table if it gets nasty. So actually, this is how acid rain forms. Sulfur trioxide gas is a pollutant that comes out of burning coal. Coal's got mostly carbon and hydrogen, a little sulfur impurities. That sulfur impurities gets turned to sulfur trioxide. Sulfur trioxide goes up the smokestack, into the clouds. When it hits the clouds, it runs into water. When it hits the water, it reacts with the water and makes H2SO4. Okay. What's the name of H2SO4? No, because it's in water. It's sulfuric acid. That's acid rain. That's how acid rain forms. Before global warming was the big push, and before, at about the same time, the ozone hole was a big environmental issue. They're beating back the ozone hole. Acid rain was a problem. Okay? It still is. Not for us in California. We're not downwind from any power plants. All the acid rain's gone, but the East Coast has a big issue with acid rain. It makes trees die easier because they're more susceptible to frost. Changes the pH of the lake so the fish can't live. Yeah.
How acidic is sulfur?
It depends on how far downwind you are and what exactly it was like, but it can be a pH of 4. It's enough to destroy the marble statues in Greece. They're all being washed away. They got to cover the Parthenon because the Parthenon acid reacts with calcium, reacts with marble. It just washes it and rinses it away. So all the ancient statues are getting rinsed away, killing plants and fish. It's a big issue. So we've got to keep SO3 from going up the smokestack. Okay. Now, of these, I would expect you to be able to predict the first one. If I have just two elements, it should be pretty easy to predict what they're going to make. For example, Mg plus N2. First of all, you can recognize this is a combination reaction because the only way that an element and an element can change is by coming together. If I got separate pieces, the only way they can change is coming together. That's how you recognize this as combination, is it's two elements. They're going to come together. That means I'm going to put the magnesium first because it's the metal. Nitrogen second. I'm making a compound, so I got to worry about charge. Mg's 2 plus, 2A. Magnesium's 3 minus, root 5A. So it's Mg 3 and 2. And then to balance, I'll put a 3 in front of Mg. Why 2? 3. I should check. 3 Mgs, 2 Ns, 2 Ns.
So you're saying no longer need the chart?
I said you had to use the chart on that assignment because I wanted to make sure you could use one when you got to one that was nasty. So, what's this going to make? If you react calcium and chlorine, what are you going to make? Ca and Cl. That's the pieces in the right places. Now I worry about charges. Ca is 2 plus, Cl is 1 minus, CaCl2. The 2's there because of the charge, not because there was a 2 on the other side. I don't copy that 2. This 2 is here because it's diatomic, unlike calcium, which is not diatomic. So that now says calcium and chlorine make calcium chloride. What? It just works. Fe and O2. This time I wrote that it made iron 3 oxide. How come I had to tell you what it made this time?
Because iron could be a bunch of different.
Charge of iron can be different. Sometimes it's 2, sometimes it's 3. So this time it told me it was 2. Wow, that's ugly. Wow. It's not just ugly, it's too ugly. So I got to put the Fe in front of the O. The Fe is 2 plus, the O is 2 minus. That adds up to 0, so that's the right formula. Yeah, it's about to be too ugly. Because there's 2 O's, so I got to put a 2 in front of Fe. Too ugly. Too fail. Okay, so first I put the pieces in place, then I use charges to write the formulas, and then I balanced. Get used to that pattern. Don't try to balance by copying subscripts. Remember, that's the mistake people make. Not figuring out the right subscripts. You got to write the right formula first. So, Al and O2. I recognize this is combination because it's 2 elements. What people are going to be tempted to do is write AlO2 right away, and that's wrong. Don't copy the subscripts, figure them out on the other side. Al is 3 plus, O is 2 minus. Al2O3. First step, write the formula. And then go to balance it. So I put a 2 in front of Al. These are my 2 Als. Now I got 2 O's on one side and 3 O's on the other. Even and odd. So I fixed it by doubling. Notice I never said put a 2 in front of whatever's front. Double whatever's in front. So if I change this Al to a 4, okay, it's going to force me to write a 2 in front of Al2O3, which gives me 6 O's, so I can put a 3 in front of O2. So that's why I never said just write a 2 in front of what's ever in front, double what's ever there. Okay. So first write the formula, then balance. And as I said, also called a synthesis reaction. Because when you synthesize things, you take stuff together and make something new. That's what happens if 2 elements go together. What if you combine, if I tell you it's a combination reaction? So you got 2 compounds and I tell you it's combination. You won't be able to tell it's combination, but I could tell you it's combination. That means I got compound and compound. That means I've got a bunch of capital letters. This one has 2, this one has 2. So at least, on the other side, at least I'm going to have 3 capital letters. Because if their polyatomic ions have O in them, right? And that's just it. I'm going to have at least 3 capital letters. And the only ones we know to write formulas for with 3 capital letters are polyatomic ions. Yeah, all those molecular ones. C6H12O6. But we don't know how to, I mean, we can't predict those formulas. Because carbon and hydrogen and oxygen come together in so many ways. Okay. So they tell me this is combination, CO2 plus H2O. So I'm going to have 3 capital letters on the other side. So I got to figure out what polyatomic ion I can make out of CO2, H, and O. Okay, hydrogen carbonate. But that would mean that's HCO3 minus, but that would mean I need a positive piece in front of it. Is there a positive piece I can put in front of that? No. So HCO3 minus is out. How about hydroxide, OH? Ever see how I can make a hydroxide out of this? Got H and O. But what would be the positive piece in front of OH? Because OH is negative, you're going to have a positive piece. Any positive piece that you can think of? Okay. What other polyatomic ions? How about just carbonate? CO3, 2 minus. Is there a positive piece I could put in front of CO3 2 minus? How about H? So I know I can make this in CO3 2 minus, H2CO3. If you do this right, they will be really easy to balance. Compound ones will be really easy to balance. Like, now we're done. 1C, 1C, 3 O's, 3 O's, 2 H's, 2 H's. So you got to be able to recognize the polyatomic ions. That's why it's at the memory part of it. Because then you'll run into things like this one. H2Cl2O7. H2O plus Cl2O7. Water and dichlorine heptoxide. We try hydroxide again, but that's not going to work because there's no positive piece. Well, actually, it's all the chlorines, right? I've got 4 to choose from. I got ClO, ClO2, ClO3, and ClO4. Which one makes the best choice for this one? Well, if you look, I got 8 O's and 2 Cl's. So the best choice would be the one that had that ratio. So Cl2O8 would be ClO4 minus. Everybody see I picked that out of all my possibilities? The one that matched up best. And what positive piece can I put in front of it? The H. And H is 1 plus and ClO4 is 1 minus. Okay, so that's the right formula. And I said they'd be easy to balance. I have 2 H's, so I put a 2 there. That gives me 2 Cl's and 2 Cl's. And 8 O's on this side, 7 and 1 is 8 O's on that side. They should be really easy to balance if you put them together right. If you have trouble balancing it, you got the wrong polyatomic ion.
I'm sorry, can you explain why, like how you came to know that?
Okay. Okay, so let's look and see. I have 2 Cl's and 8 O's. Cl2O8. Which of those best matches up with Cl2O8? For clay, because it's got the same ratio. Makes sense? It may not match up perfectly, but it'll have the same ratio. All right? That was type number 1. Was that an awful world? Okay. Type number 2, decomposition reactions. What happens to something when it decomposes? Breaks down and falls apart. What do you think happens in a decomposition reaction? They break down and fall apart. So you start off with 1, and you end up with more than 1. That means you're going to have to tear things apart, which means breaking bonds. Usually, these take energy. Breaking things apart usually takes energy. So for example, if I take liquid sodium chloride and pass electricity through it, I can separate the sodium from the chlorine. This is how Dow Chemical made all its money. Just running that reaction. They make a whole bunch of chlorine compounds. And it bothers me it's not balanced because my 2 Cl's on my product side means I need 2 Cl's on my reactants, so 2. And it gives me 2 NAs, so I gotta put 2 there. Okay, CaCO3, arrow triangle, when heated, makes CaO and CO2. CaCO3 is limestone. CaO is lime. That's the name for the mineral, lime. Because if you heat limestone, you make lime. And lime was one of the first parts of making cement. The Romans figured this out. They heated up limestone to make cement so they could build all their structures. we can predict the products if it's a binary compound. Remember what binary means. Binary means two, so just two elements. So if you only got two elements and it falls apart, what you're going to fall apart into is those elements. For example, if you pass electricity through water, what would you make? What elements are in water? H and O. Can H be by itself? No, it gets a 2. Can O be by itself? No, it gets a 2. And then we balance that. Got to put a 2 in front of water to get my 2 oxygens. It gives me 4 hydrogens, so I put a 2 in front of H2. So that's what the balance equation says. These are not supposed to be letters on pages. They're supposed to be description sentences that describe the world. If you pass electricity through water, you make hydrogen and oxygen. Okay? So if you look, I've got different amounts of gas. There's this much gas on this side and this much gas on that side. Why would I make different amounts of gas? Which gas should I make more of? How much should I make? About twice as much. Okay, so the size-wise tells me that those, one side's hydrogen, the other side's oxygen. But I don't trust just maybe some gas leaked along the way. I don't trust that. So what I'm going to do is I'm going to check it. And the check is pretty simple. There's one property of hydrogen that's pretty known, is that hydrogen is flammable. Another property of hydrogen is that it's less dense than air. So if I let it out into here and leave it upside down, just stay in there, right? And then, and actually, look at the test tube. It's wet on the inside. Because what do you get when you put together hydrogen and oxygen? Water. How are combination and decomposition related? The reverse of each other. Well, yeah, I got another sample. I didn't take it all out. It's my favorite sound. You'll get to hear that sound over and over again. Okay, so I collect the gas. Okay, so and the inside gets wet from the water you made. Now, that is proof that one side's, but how do I know it's not both hydrogen and oxygen in there? Well, because the thing about oxygen is oxygen makes things burn well. So I'm going to take this toothpick that I got just glowing and let some oops, I let it go out too far. Got to get a bigger coal. So I get it burning. Oops, still no coal. Cheap toothpicks.